Okay, so a little bit of transition metal chemistry now. First of all, these electron configurations. Remember, for transition elements, they always start 1s2, 2s2, 2p6, 3s2, 3p6. You can use your periodic table to remind you of that. If you just scan through the first 3 rows, they fit that pattern, and that will help you get that right. In the 4th row there, you've got to be careful, because you have 2 elements in 4s, and then you have 10 elements in 3d, and 6 elements in 4p. So for most of these elements, you can just work out what the configuration is just by counting how far across the period you've gone. But there are 2, copper and chromium, which don't fit the pattern, and therefore those ones you need to specifically learn what's odd about them. So chromium, if you count it, is the 4th one across in the transition series. So what you might expect it to be is 3d4, 4s2, but you have to learn that no, it isn't that it borrows an extra one from 4s and puts it into 3d, so it's 3d5, 4s1. And copper does the same thing, though for a different reason. So where you'd expect it to be 3d9, it's actually 3d10, and again only 4s1. So that's chromium. Chromium 3+, what you have to remember in that case, and again this is true for all transition element ions, is that they always lose 4s first. It's hugely important that you remember that. So the 4s comes out, and then as well as that, as many 3d electrons as you need to reach the overall charge. So in this case 1+ takes the 4s away. To reach 3+, we need to take 2 3ds away as well. So we still have all of these inner subshells filled up, but we now have only 3d3 in that subshell there. Okay, so now we're on to some half equations. So we've got zinc going to zinc 2+, and that obviously needs 2 electrons to balance up the charges. So the important thing with half equations is that the charges on both sides must balance, as well as obviously the atoms. And in that case you needed that number 2, so that the 2+ is balanced by the 2-. When we get to the dichromate one, we've got Cr2O7 2- plus some H plus some E-, going to Cr2 plus H2O. If you've done lots of other examples which include dichromate, what you will have got used to is the formation of Cr3 plus as the product. So it was very important that you notice this one was different. If you have a strong enough reducing agent, you can take the chromium down below the Cr3 plus that you normally get and go all the way to Cr2 plus, which is what you got here. So there was a slight nastiness there, that if you happen to know the usual equation for dichromate, it was actually wrong. So you just work it out from scratch. We've obviously got 2 chromiums there, so we're going to need 2 Cr2 plus. We've got 7 oxygens to get rid of, and that requires us to have 7 waters. That gives us 14 hydrogens, so we're going to need 14 H+, and it's the number of electrons that's different from usual, because to balance up the charges, we've got 14 plus and 2- is 12 plus on the left hand side at the moment, and we've got 2 lots of 2 plus is only 4 plus on that side. So to balance up the charges, you can see that we need 8 electrons. So that we get 8- and 12 plus takes you to 4 plus overall to balance that. So that's your other half equation. Okay, and then it says construct the overall equation. So in order to do that, remember you need to have the equations written so that you've got electrons on the left hand side in one case, right hand side in the other, and you have there, so that's fine, that's going the right way. But you've also got to have equal numbers on both sides, and that's not the case yet. So what you have to do is multiply that top equation by 4, because if you do that, let's do that in a different colour. If you multiply the top equation by 4, you get 4Zn2 plus from 4 zincs, but you then get 8 electrons as well, and that will cancel out the 8 electrons there. And then you simply add everything together. So you get Cr2O72 minus, plus 14H plus 4Zn, going to 2Cr2 plus 7 waters plus 4Zn2 plus. And always the check to do then, to make sure you haven't messed up somewhere along the way, is check that the charge is balanced on both sides, because that's unlikely to be the case if you've messed up your equations. So we've got 14 plus and 2 minus takes us to 12 plus on the left. 2 2s are 4, 4 2s are 8, 8 plus 4 is 12 plus on the right, so that's fine as well. Okay, then we're on to part C, and we're talking about complex ions here. So if you have a complex ion and you add something to it and the colour changes, there are always two possibilities. Either there's been a redox reaction and the oxidation state has changed, or there's been a ligand substitution reaction and you've booted out the existing ligands and replaced them. And it obviously depends what you add. But if you add something like ammonia, which is what's going on here, you've come across ammonia as a ligand in the examples you've learnt, so that's going to be what's going on here too, that the ammonia is acting as a ligand. So the answer is it's a ligand substitution reaction. Then we've got to write an equation for this reaction. You've got to be slightly careful here because you've got to get the formula of the complex that's formed correct. So here's our starting point, chromium H2O6 2 plus is our starting point, sorry 3 plus it is this time, we've changed to the 3 plus state, and that's going to react with ammonia to give us this new complex. Now the question is how many ammonias go in there. With copper 2 plus that you should have learnt, remember only 4 ammonias go in and 2 of the waters stay there. That's not the case with other transition elements, and the reason you know that is because of what they call it in the question. So you have to read the question carefully, but it calls it a hexaamine, and that hexa tells you that there are 6 ammonias going in there. So that was about reading the question carefully and interpreting that name. Hexaamine was meant to suggest to you 6 ammonias. So what you get actually is CrNH3 6, which will also be 3 plus because you've just replaced one set of neutral ligands with a different set, and 6 waters come out, and obviously we needed 6 ammonias to go in. So that's your equation. Again, always check if state symbols are needed, but they're not, so that would be fine. Part D. First of all, straightforwardly it asks us what's meant by a ligand, and the answer is it's a molecule or ion which uses a lone pair of electrons to form a coordinate bond to a metal ion. You can say dative covalent bond instead of coordinate bond if you like, because they mean the same thing. Okay, then how is this picolinate ion able to act as a bidentate ligand? So you need to remember, first of all, explain what a bidentate ligand is. So a bidentate ligand forms 2 dative covalent bonds to the same metal ion. But to get the second mark, you need to be able to explain how it's able to do that. And this is an important kind of question because they're quite keen on asking you questions like this. So what you have to do is to remember that in order to form a dative covalent bond, you need atoms with lone pairs of electrons on them. And that's generally going to mean nitrogens or oxygens or halide ions. So in this case, that nitrogen has got a lone pair, and those 2 oxygens have also got lone pairs. That one's got 2, that one's got 3, but it doesn't really matter how many they've got, because 1 will do. And so the idea is that it could use that lone pair and that lone pair to form a dative covalent bond to the same metal ion. They would also actually allow you to suggest that the two oxygens can each provide a lone pair. So that one and that one. But you've got to make a suggestion. So either say the nitrogen and the O- each has a lone pair which can form a dative bond, or that the two oxygens each has a lone pair that can form dative bonds. So you've got to be a bit more specific like that. They're getting very keen on giving you organic ligands that you've never seen before, bidentate ones, maybe even tridentate ones. So remember to spot nitrogens. If they've only got 3 bonds in the structure, that means they've got a lone pair available. Oxygens, particularly if it's O-, neutral oxygens not so good, but it can do it, as in water. But O- particularly will have lone pairs available to form dative bonds. Okay, and then we get to this stereoisomerism question. This is one of these questions where the principle is something that you should have learned, and so knowing what the answer is should have been quite straightforward. The question is how much detail you need to actually go into. So let me remind you of the principle first of all, which is that if you have 3 bidentate ligands in an octahedral complex, that the mirror images of those complexes are non-superimposable, so they're different compounds. So if you've got 3 bidentate ligands, and let's just represent them like that for the moment, okay, where each of the blobs represents the atom with its lone pair of electrons, the point would be that that complex, which would have no charge because the 3 negative charges on the picolinates would cancel out the chromium 3 plus there. If you draw the mirror image of that over here, so that to get the mirror image, you just notice that that one's pointing far away to the left, so on the mirror image it will be pointing far away to the right. This one's pointing sort of down to the southeast, so this one will be pointing down to the southwest, and this one will be up there. So those are the 2 mirror images. These ideally should have arrowheads on them because they're dative bonds, although they tend not to worry too much about that, so don't worry excessively about that, as long as you remember they are dative bonds. But the crucial thing is those are non-superimposable. So the issue is, can you get away with just representing the bidentate ligands like that? And the answer is, well, you don't really know. It doesn't tell you you can do that in the question. So ideally what you do, if you've got time, is you draw these out properly. So let's have a go at that, and what we'll rapidly see is that it's going to be quite a time-consuming task. So this one on the right there, we're going to have our nitrogen and oxygen here. So we've got that, and there's our picolinate anion. Remember that you don't put the O- on there because you add up the 3 negative charges from the 3 oxygens with the chromium 3 plus and put the overall charge, which in this case is 0, outside the bracket. So don't put individual negative charges when you draw the ligands on. So there's one of them. We can do another one the same way. So we'll have O there, and then again the ring structure around it, and finally we'll have one up there, and again, sorry, if we put nitrogen there and oxygen there, we can slightly messed that one up, but you get the general idea that those are your 3 ligands. Now that's quite complicated, and they didn't expect you to actually draw all of those out. If you only drew this, and explained that those are the two possible isomers and that they're non-superimposable mirror images, meaning that they have the same connectivity of bonds but a different arrangement in space, so they're stereoisomers. If you explain all those ideas, you get the 3 marks. What I would have done, I think, is drawn at least one of these ligands on, connected up like that, so that they can see, yeah, you do understand how that can act as a bidentate ligand, but maybe not bothered drawing all these ones on and all the ones in the mirror image and just represented them like that, because it's going to take you too long. So, you know, you have to make those strategic decisions, but I think if you've shown that, yeah, you can see how one of them can act as a bidentate ligand, you can then just represent all the others in this shorthand way. In fact, though, if you represented them all like that, you still got the marks, but don't count on that. You know, they're not always consistent on that kind of thing. And on then to part E, which is one of those identifying what the compound is from various bits of data question. So it brings in various kinds of mole calculations. So you need to be ready for questions like this. You know, they're not specifically based on stuff that was in this module, but remember, that's fair enough. The A2 rules are that they can bring in ideas from last year, and particularly when it's very general things like mole calculation methods, they will do that and assume that you can still use those methods. So let's have a look at how this one works. Starting point is an empirical formula calculation. Those are very common, so make sure that you haven't forgotten how to do those. So the simplest method is to set up a table with your 4 elements across the top. Okay, and just copy down the masses or percentage masses. If they're actual masses, just do it the same way, but here they're percentage masses. So we get 11.11, 3.17, and 41.27, and 44.45. And then remember, the trick is that you divide those by the relevant AR. So you divide the nitrogen by 14, the hydrogen by 1, and so on, and you get 0.793 and 3.17 and 0.794, which is more or less the same as that one, and 2.78. And then you want to make those into whole numbers, but in the same proportion, so you divide through by the smallest of them, which is 0.793. So you divide that by itself and you get 1. 3.17 divided by that is 4. That one's more or less the same as that, so that's going to be 1 again. But this one comes to 3.5. It doesn't actually give you a whole number straight away, but you can see easily now that you can still keep them in the same proportion and get whole numbers by simply doubling them all, so that you get 2, 8, 2, 7. And that gives you the empirical formula, which will be N2, H8, Cr2, O7. Okay, now, then it says deduce the ions that make up the ionic compound. If you look at the information in the question, it doesn't actually give you any more information to deduce what the ions are. So what it means is use your chemical knowledge to identify ions that could give you, ions that you know exist, that could fit that empirical formula. So when you see nitrogen and hydrogen, the obvious possibility is that you could have ammonium ions, NH4+, and you can see N2H8 corresponds to 2 lots of NH4+. So that looks like a good bet. And what does that leave? Well, it leaves Cr2O7, and to balance up the charges, if you've got 2 lots of NH4+, that's 2+, this must be 2-. So if you'd never heard of that ion, you could deduce what it must be in order to balance the charges out. But if you look back earlier in the paper, even if you haven't come across it before, there was a question which had that very ion in it. So hopefully it would be fresh in your mind that the dichromate ion exists, and that's what its formula is. So those were the ions that it wanted. You didn't necessarily need the 2 there. Those are the formulae of the ions. Okay, so it's about using chemistry that you know, sometimes clues elsewhere in the paper, to just think of ions that actually exist that could be put together to make that formula. Then we've got to identify substance B and substance C. So let's look at the information we've got for that. It tells us that B is a chromium oxide, and the only information it gives us is that the MR is equal to 152.0. Okay, molar mass, remember, is the same number as the MR, it's just with different units. So that's the MR, and that's all we know. So the question is, how do we figure out the molecular formula? Well, you've got that chromium has an AR of 52.0. So there are actually only 2 possibilities for the numbers of chromium atoms in the formula, because if you had 3 of them, that would already take you to 156, which is too much. So it must just be 1 or 2 chromium atoms. So let's try 1 times chromium, which gives you 52.0. If you take that away from 152, you obviously get 100. And you just ask, well, can you fit in a number of oxygens in order to get a mass of 100? And the answer is no. So you say 100 is not a multiple of 16, because each oxygen weighs 16, so that won't work. So let's try 2 chromiums. So 2 lots of 52.0 adds up to 104. If you subtract that from 52, you get 48, and now we're in business, because 48 is equal to 3 times 16. So that means that we are going to have 2 chromiums and 3 oxygens. So Cl2O3 is the formula. Okay, so when you get questions like that, where the only information you have available is the MR, generally it will involve some fairly heavy element, where you don't have that many possibilities for how many of those atoms or ions of that element there are in the formula. And so you can fairly quickly exclude one, narrow it down to the other one. So Cr2O3 is the formula of B. Substance C, it tells us, is a gas, and we're told the mass of 1 cubic decimeter. So as soon as you are dealing with gases, the relationship you're likely to need is moles is equal to volume in dm cubed divided by 24.0. So when it says that the each 1 dm cubed has a mass of 1.17 grams, what we can do is figure out how many moles that is. Okay, so 1 dm cubed is equal to 1.00 over 24. Okay, 1 dm cubed, which is 1/24 of a mole. You could work that out as a decimal fraction if you wanted to, although as it turns out you don't need to, so we'll just leave it like that. And then you say, okay, now we know how many moles we've got, and we know the mass, so we can just go MR is equal to mass over moles, which is 1.17 grams divided by 1/24, which is 1.17 times 24, which is 28, is the MR. So it's a gas with an MR of 28 that's formed from that compound N2H8Cl2O7, and 28 you should fairly quickly spot is 2 lots of nitrogen. So C is N2 is, I think, the only possibility that you can really come up with out of those elements. So C is N2. So now we know most of what we need to know in order to put this equation together. So if we write down the formulae we know, our starting point was NH42Cl2O7. You could just write down the empirical formula there if you wanted to. That would be fine. It's decomposing, it tells us, so it's not reacting with anything else. Remember, decomposing means just breaking apart, like that. And it's giving us nitrogen, which was compound C, plus Cr2O3, and it tells us, does it tell us anything else? Yes, it tells us that we get water as the other product. Okay, so then we've just got to set about balancing that. So we've got 2 nitrogens, which means just 1 N2, so that's okay. We've got 2 chromiums, which gives us just 1 Cr2O3. So the question is, how many waters? Well, if we add up what we've got left, we've got those 8 hydrogens, and we've got 4 out of those 7 oxygens left. So it's 4 H2O is the answer. And that's the end of the question. So that's quite an important example of a kind of question they like very much. So using very simple mole calculations from last year, plus a little bit of chemical knowledge, and again just keeping all that information together, not getting lost as you work through it all. So if you didn't get that one right, try and work through it and think of the kind of tricks that helped you in order to get to the answer, because that's the sort of thing you're likely to have to do on another occasion. Okay.